What's going on, everybody? Mr. Gustin here. I'm going to walk you through some notes that are associated with worksheet 15 and symmetric angled launches and addition of vectors and velocity vectors. So these are some notes I would take at the very top of worksheet 15 if I were you. Okay? The first thing I want to do is redefine what a vector is. Remember, a vector is something that has a direction and a magnitude. One of the most basic vectors we've talked about in this class is the displacement vector. We've also talked about two different directions at this point. We've talked about the x direction, or the horizontal direction, and the vertical direction, or the y direction. Both of these directions our objects can move in. Other kind of coordinate systems would include north, east, south, west, up, down, left, right, different coordinate systems that have different directions associated with them. So what I want to do here is talk a little bit about the displacement vector and how we can add them together. So I want to start by talking about adding vectors. And we'll get into more about other vectors that we can add, but right now I want to talk about specifically adding displacement vectors. We'll start with an example problem. Let's imagine that I start here at point A. And I move from point A, or an object moves from point A over to point B. And that is, let's say 10. Let's say that is actually, I don't want to say 10. Let's say it's 8. 8 meters away. And then I make a right-hand or a downward turn, and I walk 6 meters down. And I ask you two questions. I say, one, what is my distance? How far have I traveled? The second question I ask, what is my displacement? Now, because I made a turn and it's not a straight path, there are two different answers to this question. First, let's handle distance. We know distance isn't a vector. Distance is based on the path the object moves. So if I travel from A to B, and that's 8 meters, and from B to point C at 6 meters, well, the distance I travel is going to be 8 plus 16 meters. That is going to be 14 meters total. That is my distance traveled. But displacement's a little different. Displacement asks, how far have I moved from my initial position? So how far away am I from A when I am at C? Well, that question has a little more complicated of an answer, because I'm not 14 meters away from C, or from A. I'm kind of at this weird angle here away from A. And when I figure out, I draw a straight line from A to C, what I see is I actually have created this right triangle. And because I know a little bit about trig, I can find what this vector is, what this length is. Okay? We can go ahead and use the Pythagorean Theorem. We can say that our displacement, our change in x, change in position, is going to be equal to 8 meters squared plus 6 meters squared. And actually, this is our displacement squared. Do you see the Pythagorean theorem there? Do you see my a squared plus b squared equals c squared? That's what I've done here. To find the length of this side, I've gone ahead and used my Pythagorean theorem. I think this is one of those special triangles that ends up being 10 meters. I think it's a 3, 4, 5 triangle. So to answer my question, I have moved 10 meters from A to C. That is the magnitude of my displacement. I can also go ahead and find the angle of my displacement right here. If I want to say at what angle did I move to the right or towards C, I could find that angle in one of two ways. I suppose 3 ways. I could use any inverse trig calculation to find that. So just to refresh your memory, a little SOHCAHTOA, opposite over adjacent. So this would be 6 meters over 10 meters. Cosine would be 8 meters over 10 meters. Or I suppose we could do tangent and have that be 6 meters over 8 meters. Any one of these calculations, any one of these inverse trig calculations would allow you to find the angle. You could go ahead and say it was 10 meters at this angle to the right. That would be a way I could find my displacement. Let's try a second example. Again, we're going to still work with displacement and distance. Let's imagine I start at point A. This time I walk 10 meters forward. I go ahead and I walk 3 meters downward. And then I walk 6 meters backward all the way over here. We can call this B, we can call this C, and we'll call this D. And I ask the same questions. What's the distance traveled? And what's the displacement? Again, the distance is the path I traveled. I went 10, and then 3 meters, and then 6 meters. My distance is 10 meters, plus 3 meters, plus 6 meters. It's a total of 19 meters traveled. But my displacement's a little different. My displacement is where I start and where I finish, and the difference between those two. Let's go ahead and make my right triangle. I moved, you can see, this far down and this far over. What are those distances? Well, it was 10 meters forward and then 6 meters back, which means I've netted 4 meters in the right direction. Vertically, I've netted 3 meters. How far have I moved? Well, I can go ahead and do my Pythagorean Theorem again. My 4 squared plus my 3 squared equals c squared. But I also know this is one of those special triangles where my total displacement is going to be 5 meters. Okay, so I've been adding some positive vector, subtracting my negative vector, and I still end up with just the same basic concept we've had all unit long, taking the difference in my initial position minus my final position. So now I want to move on from adding vectors into separating vectors. We've been talking about projectiles and launching things through the air. Well, down below, we're about to talk about what happens when I launch something at an angle. So let's imagine I launch something here at some angle theta above the ground, above this horizontal. I'm going to call this velocity my initial velocity. Now my initial velocity is both in the x direction and in the y direction. You can see that right here. Here is my x component of the velocity, and here is my y component of this velocity. I'm going to call this Vy, and I'm going to call this right here Vx. Next door to it, I'm going to go ahead and draw a right triangle as if you'd see it in trigonometry. I would call this A, I can call this B, and I can call this C. Here's theta. Well, let's look more closely at how I might use trigonometry to find my initial x velocity and my initial y velocity. If If I look at my trigonometry triangle here, I know that I've got three trigonometric functions. The cosine function, the sine function, and the tangent function. Cosine, if you follow the SOHCAHTOA rules, cosine is always measured as the ratio between the opposite side, the adjacent side, divided by the hypotenuse. So in this case, that would be A divided by C. That ratio is known as cosine theta. For sine, sine is typically, or is always, the opposite side divided by the hypotenuse. In our case, this would be B over C. And tangent is the ratio of the opposite side to the adjacent side, B over A. We're going to carry those ideas over here to figure out how I might use my initial velocity and this angle to find these two vector quantities. Let's look. Vy exists on the opposite side of the triangle from my theta. So the opposite side must mean I'm using a sine function to figure out my Vy. So sine theta of this triangle is going to be equal to Vy over the hypotenuse, which is initial velocity, or V0. Let's look at Vx. Vx is the adjacent side to this angle. The adjacent function is the cosine function. I can use cosine of theta equals Vx over the initial velocity, or V0. This is great, but I want to write them in a little bit more useful way for us. So I'm going to use a little algebra to rearrange them. What I'm going to do is, instead of calling sine theta equal to Vy over V0, I'm going to write these like this. V initial times sine theta equals the velocity in the y direction, initially. For the horizontal direction, V initial times cosine theta equals Vx. Now, these two equations are not equations that you will find on your equation sheet, but they are important relationships to have that come from our understanding of separating vectors from our vector triangle. I want to go ahead and work through an example problem with you here on the bottom. Let's do that. I already have a model drawn for me here. It says a soccer ball is kicked with an initial velocity of 5 meters per second at an angle of 36.9 degrees. So here's my angle. There it is. It's kicked with an initial velocity equal to 5 meters per second. There's my angle, which I know is 36.9 degrees. List all of the variables you can determine their values without using any kinematic equations. Fantastic. I'm going to go with my initial stuff right off the bat. Initially, I know that the acceleration in the y direction, because it's in free fall, is baby g. That's negative 9.81 meters per second squared. That I've got down in my head. In the x direction, I know there's no acceleration. Acceleration equals 0. I know that my velocity in the y direction at the top, Vy at the top, 0 meters per second. That might be about it in terms of things I remember off the top of my head. But it doesn't say I can't use any equations. It says I can't use kinematic equations. So what I can also still figure out is the initial velocities in both the x and y direction. Let's go ahead and do that. We just wrote this down, didn't we? We just said that the initial velocity times cosine theta equals the initial velocity in the x direction. And we said that the initial velocity in the y direction, the initial velocity times sine theta equals the initial velocity in the y direction. I can go ahead and solve for these. Let's do it. You calculate using our numbers here what the initial velocity in the x direction is and the initial velocity in the y direction is at home, and I'll do it here as well. I would make sure my calculator is in degree mode right now. I get that my initial x velocity is equal to 4.0 meters per second. I think I know what this one is off the top of my head now. Initial velocity in the y direction is going to be equal to 3.0 meters per second. Okay.